Alright, so this video we're going to do sort of the opposite of what we did in one of the earlier ones, and we're going to work backwards and use the pH to calculate the Ka. And so we're going to set up the same problem that we did before when we were using the Ka to calculate the pH, except we're going to solve it backwards. It's also a good way to practice problems. If you have one that you can sort of work forward and get to the answer, you can then try it in different ways and make sure you can get back to what the original case was. So as long as you have two of the three of pH, Ka, and initial concentration, or some way of settling that, then you can work backwards and figure it out. Figure out the third, that is. So in this case, we're looking at the Ka of a 0.1 molar solution of HCN if the pH is 5.15. So I'm just going to set up like we did in the previous video, and we're going to say that HCN aqueous is going to go at equilibrium into H plus and Cn minus. Okay, and when we take a look at the H plus and Cn minus, we're going to set up a Rice chart because this is not a strong acid, so we're at an equilibrium. Okay, the initial 0.10, 0, 0, the change minus x plus x plus x. So at equilibrium, this is 0.10 minus x, x, and x. Now, the other piece of information we're given here, we're trying to find the Ka. We don't know that yet, but we're given the pH. Okay, the other thing you could be given here would be percent ionization. In either case, it doesn't really matter. We can work backwards from that and use it to find X. So we're going to set up that since the pH is equal to, move this out of the way, since we know that the pH equals negative log of concentration of H plus, we know therefore that 5.15 is the negative log of H plus, and therefore I'm just going to move the negative over, negative 5.15 positive, take the antilog, so 10 to the negative 5.15 equals concentration of H plus, which actually comes out to be 7.1 times 10 to the negative 6th. A little bit different than the previous one, and the reason for that is simply that we had to round earlier to negative 5.15 was really 5.154. If you do 10 to the negative 5.154 in that case, you get closer to 7.0, but we'll go forward with this. Oops, lost part of that there. Alright, so the 7.1 times 10 to the negative 6th that we have, okay, is the equilibrium concentration of H plus, and therefore it is X. Okay, so it's going to be X in all of these cases, and therefore we can plug those in and use it to solve for the Ka, because we know that the Ka is equal to, I guess we're going to write it all out here, concentration of H plus times concentration of Cn minus over concentration of HCN, hydrogen cyanide, and that therefore is going to be x squared over 0.1 minus x, which in this case is going to be 7.1 times 10 to the negative 6th squared divided by 0.1 minus 7.1 times 10 to the negative 6th. Okay, so we plug that through, and we're going to come out with 5.0 times 10 to the negative 10th. Now note this is a little bit different than the one that we found before, and again it has to do with just rounding to significant digits. If I had carried more digits all the way through going forwards and then backwards, it would have gotten the same thing, but instead of 4.9 times 10 to the negative 10th as my Ka, I'm looking at 5.0 times 10 to the negative 10th, but that's just a difference of rounding right there, so there we go. This is how you'd use pH to find Ka.